Okay, so the beginning of 2.7, I'm gonna sort of do this in a weird way. It's called the rational root theorem, but the premise is, and you already know that I like guessing and checking, is imagine if I asked you to just guess and check with this problem. There's so many different possibilities. Now, there's only one way of getting 3x squared, and that would be 3x times x. But there's a lot of different ways of getting negative 6. You could do 1 times negative 6, or, keeping everything the same, it could have been negative 1 times positive 6. Now, only one of these answers is correct as I lay out all the possible ones. And if you want to be kind of a stickler about it, like this is actually the correct one, because you get 18x minus 1x to get 17x. But I'm not asking what the exact answer is. I'm asking for possible. So I'm sort of ignoring this middle term right now. Like, I really don't care. And because we're going to get into cubics and quartics and quintics. And it's not really a methodical thing. It's just a guess and check. The other part of this that I want to point out is that, while I'm leaving the 3x and the x alone, I could have switched the 6 and the 1 around, plus and minus. Or 3x minus 6, x plus 1. But as you notice the possible roots for this problem, I'm going to assume that you can do this quickly in your head where you find your zero product and do negative 1 over 3. This would have been positive 6, but then down here it would have been positive 1/3 and negative 6. Well, down here, if you did this problem, it would have been negative 6 divided by 3 reduces to negative 2, positive 1. This one would have been positive 2 and negative 1. But even all of those possibilities are not it, because I didn't have to use 6 and 1. I could have done 2 and 3, plus 2 plus 3. Because 2 times 3, whoop, I didn't want a plus there. I wanted 1 to be minus, sorry. 2 times negative 3 would give me 6. But again, I didn't have to make the 2 positive. I could have had the 2 be negative, and then the 3 would have been positive. Or I could have had the 3 over here and the 2 over here, but same idea, is the 3 could have been negative and the 2 could have been positive. So as I'm looking at these possible roots, it would have been negative 2/3, positive 3, positive 2/3, negative 3, negative 1, positive 2, positive 1, negative 2. Now there's a few things that you should notice by the possible roots. That's why it's called the possible rational root theorem. These are all rational numbers, by the way. Rationals are a ratio. If I haven't explained that before, that's what these are. And there's a couple things I should be shouting out at you. One is that all of the answers happen as plus and minus. We had every positive answer we had. We also had a possible that was negative. For the record, as I mentioned earlier, this is the correct answer on this problem. The other thing that I should shout out at you is all of these numbers are factors, 1, 2, 3, and 6, of 6. The other thing that should be shouting out at you is that all of the denominators that we're looking at, 3, and technically there's another denominator of 1, are factors of this number. And that's what we're going to get into on this problem. So what are the factors of the constant term? 1, 2, 3, and 6. By the way, the constant is the plus 6 in the problem, or is it minus 6? It doesn't matter. And then the leading coefficient, which was 3 in the problem, were 1 and 3. As you notice, all of the possible answers, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, and then also plus or minus 1/3, plus or minus 2/3. Why do you think I don't have 3/3 written down? Well, let's think about it. 3/3 is equal to 1. Well, we already wrote down 1. And what about 6/3? Well, 6 divided by 3, that's 2. We already wrote that down, so you don't have to write it twice. So the premise is this. And so as we get to the rational root theorem, I guess what I should do, I'm not going to go to a graphing calculator, even though that's what it says to do. What it breaks down to is that the only possible rational roots is to look at the leading coefficient and the constant. Find all the factors of those. Now they happen to be the same numbers, so you'd be writing the same numbers twice. And the only possible rational places, now it could cross the x-axis at other places with irrational numbers, but the only possible rational roots will be all the factors of the constant I guess I should be writing this in that box down there. I'll just write it right here though. Divided by factors of the coefficient, of the leading coefficient. And stick a plus or minus in front of them, because that's what it could be. So all the possible rational roots in this problem would be plus or minus 1, 2, 3. All they should have a plus or minus, but if you get lazy like I do, you can just write out plus or minus 1s. Another math teacher might ask you to do more of these. So all of these represent these numbers divided by 1. Well, now we need to take all of these numbers and divide by 2 next. So 1/2. I don't have to write 2 divided by 2 because that equals 1. But I do have to write down plus or minus 3/2. Plus or minus 6/2 is 3. Now I have to divide by 3. Plus or minus 1/3, 2/3. I don't have to write 3/3 because that equals 1. I don't have to write down 6/3 because that equals 2. And then plus or minus 1/6. You don't have to write down 2/6 because that's 1/3. You don't have to write down 3/6 because that's 1/2. You don't have to write down 6/6 because that's 1. And that is the next lesson. So again, what I just wrote up here is pretty much the same thing as what goes in this box. If you want, you can write down all the words from the answer key. Okay, so he used a graphing calculator and showed you what the most likely possible rational roots are, and he writes it out in words. And so feel free to pause this if you prefer. A list of all rational numbers that are possible roots of a polynomial function can be formed by placing each integer factor of the constant term over each integer factor of the leading coefficients. It is a very wordy explanation, but it is correct. Notice how this individual, he likes to write out plus or minus, plus or minus, plus or minus. I tend to get lazy, but this is the same problem that I just did. So I'm going to go back to the notes, so feel free to pause, write down anything you need to as I go on to the next problem. Now, what can you do to actually verify what the roots are is to guess and check. And usually that guess and check method will involve synthetic division. 6, 19, 1, -6. I'm going to cheat for a second because the answer key has the answer right there. So I don't feel like, looks like -3 is the most obvious answer. And what do we know about if something is a root or not? Think about that as we work this out. Adding straight down, adding straight down. When you get a remainder of 0, that tells you that x equals -3, or whatever was in this box was a root. Now, as you notice, now we actually have enough information to finish the problem, because now we're down to a quadratic. And we can do the quadratic formula. -b plus or minus the square root of b squared minus 4ac all over 2a. 2 times 6 is 12. So now, let's see, 4 times 6 is 24. That would be -48. 1 plus 48 is 49. Square root of that is 7. So we're at -1 plus 7 divided by 12. Give myself a little bit more room. And -1 minus 7 divided by 12. Well, this gives me 6/12, which is 1/2. And then this one gives me -8/12, or -2/3. And each of those were also rational roots that we could have guessed and checked until we get there. So the better you are at guessing, the quicker this will go, actually. And there are other ways, like using a graphing calculator to get the best estimates. So again, I like that he uses PRR for possible rational roots. It's not really a common thing, but you look for all the factors of the constant, 1, 2, 5, and 10 here. But then you also have to divide by factors of 6. So 1/2. You don't have to write down 2 halves because that's 1. 5 halves. You don't have to write down 10 halves because that's 5. But then also 1/3, because that's 3 is a factor of 6. All right, plus or minus again. Let's see, 2/3, 5/3. I think you have to write all of them this time, and then 10/3, and then also over 6. 1/6. Let's see, 2/6 is 1/3, so I don't have to write that. 5/6. That doesn't reduce, does it? But 10/6 would reduce to 5/3. But again, I'm going to cheat and use the answers. And again, as long as you have your graphing calculator, you could see what appears to work to get 0. Otherwise, it's guessing and checking. So I use the answer key to see that 2 is the whole number that works. And you only have to find one that works. As long as you get it down to a quadratic, you can use the quadratic formula. 26, that's -5, -10, and you do get a remainder of 0, so x equals 2 works. And now here's your quadratic. To use the quadratic formula, let me write over here, -b plus or minus the square root of b squared minus, let's see, that would be 30, so that becomes -120, because we're multiplying that by 4 AC, all over 2 times 6 again, 12. So that's 287. Square root of that is 17. So plus 17 over 12 and -13 minus 17 over 12. Because of the plus or minus, you split it up. So that becomes 4/12, which reduces to 1/3 is another root. And then -30 over 12. Divide both of those by 6 and get -5 halves. That's your 2 roots. There we go. Okay, I think what I'm going to do is just share with you the answer key now for these last 2. By the way, the reason why I go to this quadratic formula is not everything has been factorable. Okay, the answer key shares with you how to do this. Now he also does highly probable rational roots by using a graphing calculator, but I'm not a big fan of doing that because what if you don't have a calculator? So here's the next 2. I'm trying to fit it all on one screen. Let me just extend the screen down. There we go. I didn't like that. And I'm just going to let the video play out, and you can see how I worked it out. Notice that it's factorable on each of these, but we don't always end up with a factorable problem that you might need to resort to the quadratic formula to get your remaining roots. Again, a lot of guessing and checking, especially for number 2 here, where all of the roots were fractions. Number 3, at least you could do 2 with your synthetic to try and get that answer.